So I think we'll just sort of pick up where we left off last time. We were talking about generating simulated data. I posted the Jupyter Labs session. Someone requested that, so I posted that on YouTube if anyone wanted to download it. So there's an attachment available below the as an announcement on the YouTube video. Let's see. See if we can pick up where we left off. All right, that should be sim data, or that was something else. Okay, yeah, sim data. So that's what we were doing last time. Right, so we were reading from a PDB file, or sorry, an HDF file, which we had made from a PDB file at the command line. I did a little bit of a display test there. I guess I should probably open that display widget on my own machine again. I've got a bunch of other windows covering stuff up that you guys can't see. So if I seem to be kind of navigating over nothing, that's what's going on. Okay. All right, so yeah, so we read the volumes in, displayed the volumes, then we generated these random projections and random orientations. We're making use of the symmetry object with no symmetry imposed to generate random projections in 10,000 different orientations. And then we're writing them out to this proj.hdf file. And so in theory, we should have proj.hdf here available. I think I let it run for the full 10,000. Hopefully we'll see. Yep, 10,000 images. So, so the other thing we might want to do, so if we take a look at those, why don't we actually go ahead and do that? Let me minimize this for now. And let's run regular E3 display here for a minute and take a look at proj.hdf. And if you guys did this yourselves, then you should have something similar. So we've got our modified Groyel particles in lots and lots of different orientations. Now, we didn't do anything about centering. I didn't shift them in the box. And if we wanted to do a sort of a reconstruction, so if our goal was to make data that we wanted to test our ability to do a normal reconstruction on, then I probably would have done some random translations associated with it as well before we added data. But in this case, since our goal is to look at dynamics, and if we're just sort of testing it with simulated data, we might as well just leave it well centered at the beginning, rather than sort of artificially adding that step to the process. So we just want to look at the dynamics analysis. We're not as interested in the refinement analysis. And I guess it's sort of obvious, actually, if you look at some of these particles, you can sort of see this and this are not in two dissimilar orientations, but you actually see the missing subunit right there. So it's actually pretty visible by eye in certain orientations. You can see it there, for example, too. So I certainly hope, well, our dynamics analysis tool will be able to easily detect that. The subunit, which is moving a little bit, we'll see that may be easier or maybe more challenging to find. We'll have to see how it goes. Anyway, so we've got this data now, but we haven't added any noise to it. We haven't put any CTF on it. So if we let's see, actually we can do it with this. We just do show 2D. And that right in all 10,000 images, we can scroll through them if we like. In the control panel for the 2D display widget, there's a power spectrum button, and we can tell it to compute the mean power spectrum for the whole stack of images. So if we look at that for these just basic images that we created, what we'll see is the power spectrum. You can see there's a 1 × 10⁻³ power up here. That the power spectrum is extremely strong. There's a very sharp peak at very low resolution. And that's actually mostly the the difference between the particle and the solvent, right? So this is 0 out here, and the particle is got a fairly strong positive value. If we had this solvated in some sort of solution in water molecules or something like that, then there would be much less of a sharp density gradient, and the strength of this peak would vary quite a lot. But let's go ahead and put this on a semi-log scale so we can see a little more detail. So on the semi-log scale, now we can see, it's very strong here, but there's some other features here. The lump that we see here is at about 4.5 angstroms. This is due to beta sheets in the structure, and a little bit of a lump that we see in here. This is alpha helices in the structure. It's actually kind of interesting that we see such a strong, relatively strong beta lump in here and a somewhat weaker alpha lump, because there's actually quite a lot of helical content in GrowEL. Anyway, so this is what the power spectrum of just the unmodified particles looks like. Now, as you presumably all know, if you do a CTF simulation, if you look at the CTF of the microscope, obviously at very low resolution, there's a very strong high pass filter effect. Very low resolution features are cut off by the microscope a lot unless you're using a faceplate. So if we want to simulate cryo-EM data and we just leave it like this, it's really not a very good simulation at all, because the very strong low resolution contrast makes certain types of image processing really easy to do. So people that work with simulated data that looks like this, that doesn't take the CTF into account, aren't really testing their algorithms very well at all. Now, we could try for very, very realistic data generation. There have been several groups that have developed very realistic microscope sort of simulators over the years, which include various terms for noise and all the proper envelope functions and everything like that. Lan was just telling me that at M&M, there was someone who was using GANs to generate simulated data in material science, so type of neural network. And certainly you can do those things, but it's not really necessary to make simulated data that's that good for most purposes. But if we don't at least take the first step and put some CTF and some noise in, then we're just not going to be doing a very good test of our data. So that's what we need to consider next. So the question then becomes, do we want to add the noise and the CTF from the command line, or is it something we want to do from some sort of a GUI program or something like that? So I would say in this case, so we don't actually have a GUI program which is really designed to make properly different CTF modified data. We have E2 CTF sim. Oops, interesting. Anyway, we don't need that. E2 CTF sim, which is just a basic CTF simulator. This simulates all the standard CTF properties, but it doesn't try to do a really in-depth simulation of the whole microscope. And this program, in addition to showing the CTF in different ways, so you can show amplitude or intensity. This is probably more what you're kind of used to seeing. You can see the tone rings, simulated tone rings down here. If I grab the defocus slider, we can see what happens. We can see if we go to far from focus, you can see the moire patterns here due to the sampling present in the image, which is actually kind of similar to certain types of Fourier effects that you can produce in various ways. Anyway, we can adjust all these parameters. The default parameter here, we are using one angstrom per pixel from our simulation, so we don't have to mess with that. The default parameter here, 300 kV, and the 4.1 was actually from a Joel 3200. I think that's what that one's from. If you're using like a Krios, we could simulate 2.7 or something here, but actually it makes almost no difference at all at this level of simulation. So if you look at the curve here and watch me change it from 2.7 to 4.1, it's a very modest shift in the curve. I mean, it's almost just a little bit of a defocus-like shift. So if you change the C sub S, you can kind of almost account for it by just changing the defocus a little bit. Not really, not perfectly. It's not, in the mathematics of it, it's not exactly representable as a defocus, but for a small perturbation, you can accommodate it fairly effectively. Okay, so the things we need to pick if we want to do some CTF simulation are things like, the B factor, what defocus range do we want to use, how much amplitude contrast do we want to use, and that sort of thing. These parameters will probably fix. We'll just be, we'll be making this for one particular microscope. Now, another thing we can do from the command line with this program is you can specify some data. Oh, where is it? Apply. Yeah. So if you give it the apply option, you can give it a 2D image, and then it will apply the CTF to that 2D image in real time, so you can sort of see what the real space effects are. Again, this is mostly designed as a teaching tool rather than sort of a practical thing that you'd use all the time. But the apply thing will be a good way for us to sort of decide what values might be appropriate when we actually programmatically apply them to data. So we'll say E2 CTF sim apply, and we'll just give it that stack of particles that we made, proj.hdf file. And we'll leave everything else at the default values. That's fine. So now we should have gotten, close this a little, reduce this a little bit. We should have gotten one more window. Where is it? There it is. Okay, so there's the window with our simulated image. So now if I change the defocus, I can see the effect of the defocus on the image. You can see as I get really far from focus, the artifacts start sort of expanding outside the region of the box, and you can actually see them sort of bouncing off the wall and reflecting back into the box. So these sorts of artifacts near the edge of the box are the reason why in EMAN our convention is that we always try to use a box size which is padded by about 50% larger than the size of the particle, because we want to reduce the number of these artifacts that come in from the edge. These sorts of artifacts can actually be particularly pernicious if you're trying to do single particle reconstruction and stuff, because sometimes the artifacts can come in a way which will actually reinforce themselves in the structure, and it'll look like you're getting better resolution out of the artifacts, even though it's damaging your structure. So people who go into Relion and they because Relion suggests the same thing too, but if you look at what people actually do, they actually often use fairly tight boxes in Relion, and they're actually shooting themselves in the foot when they do that, because they're going to make their structures a little bit worse, not better, because of it. Now it will make things often run a little bit faster, and that is of course something that you have to take into account in some cases. All right, so we can pick sort of a defocus range. A typical defocus range for simulating single particle data might be something between, say, 1 micron and 2.5 microns or something like that. So somewhere from there to there. It just sort of depends on your circumstances what you might want to do. I think maybe we'll simulate from maybe 1 to 2 microns or something like that. Usually it's good to cover about a 1 micron range in your simulation. We can actually add additional curves up here. So if I hit new, I can make a second curve. And if we look at the second curve compared to the first curve, we'll see if we make, say, this one at 1.5 microns, and the first one at about 1 micron.
Could I ask a question about the higher defocus?
Yep.
When you set the defocus higher, I see additional circles showing up in the
down here
Fourier transform.
Yeah, those were the sampling, the Moire patterns that I was talking about. Yeah.
Okay.
Yeah. So basically, that's just that. If we zoom in there, you can see it's basically just an effect of the pixel sampling. So if we sampled the pixels twice as finely, then these things would vanish. So they're in a certain sense they're an optical illusion, but they can actually have some real impact in data analysis in certain cases. So there are 2 ways to avoid it. One would be, so if you had a bigger box size, so if instead of a 256 by 256 box, you had a 512 by 512 box, then you would be able to go out to a much higher defocus before you started seeing that kind of artifact. There was actually a long time when Marin van Heel was strongly suggesting, actually may still be strongly suggesting, that you do your phase flipping CTF correction on the whole micrograph rather than doing it on each particle, because if you do it on the whole micrograph, then you don't have to worry about any of these effects. I mean, you can go out to 6 microns defocus, and you still won't have any problems with that sort of issue. But there are some downsides as well to trying to correct the CTF on the whole micrograph. For example, the fact that each particle is at a slightly different defocus. So if you correct the whole micrograph by phase flipping, then you can't do per particle defocus correction anymore. So there are trade-offs. Okay, so back to what we were doing. So if we look at this, how the CTF curves interact there, let me go ahead and say intensity with sum. Okay, so now this is going to show us three curves. So we've got the one curve and the two curve, and then the black curve is the sum of the red and blue curves. And if I add a third one, I can actually see the sum of that one as well. So if you were trying to pick sort of the optimal defocus set of defocuses to use when you're collecting your data, then you might want to be kind of careful about this, because you can see the defocuses that I have here right now. So I've got 1 micron and 1.5 microns and 1 micron, is that at about 10 angstroms, there's still a coincident 0. So if you collected all your data with just those two defocuses, you wouldn't have any useful information at 10 microns, and that would, in your FSC curve, you'd see this massive dip at 10 angstroms. It used to be in the early days of single particle analysis, in Spider, they suggested when you collected your data, you use defocus groups. So you collect a bunch of micrographs at 1 micron, then you collect a bunch of micrographs at 1.2 microns, and so on. And then when you did your data analysis, you grouped all of the 1 micron images together and all the 1.2 micron images together, and you did the CTF correction inside these groups. So it required you to actually be very careful about your focusing, but it also meant that you wind up having a lot of features in this sort of sum curve. So if I adjust the third one, so it's not 1 micron, it's say 1.2 microns or something like that. You can see here, look, I'm still getting, at about 7 microns, I'm still getting one of these features. And here too, sorry, not microns, about 7.7 angstroms, and at 7 angstroms, there are still these near kind of coincident zeros where we have less information. So trying to pick a small number of defocuses and actually having it produce a somewhat smooth curve is actually kind of tricky to do. Now, when people are working in, say, negative stain, they actually use a very different trick. They'll actually go very, very close to focus. It's so-called Schetzer defocus. So if we do that, if we get down very close to focus, I don't have a good way of turning off the other curves. I'll just zoom in here. But if we look at the green curve here, and if we add a little bit of amplitude contrast, which we probably should have done already, let me set, say, 10% amplitude contrast. That's a pretty typical value. I'll put 10% in on all of them just to make sure. So if we put 10% amplitude contrast in here, you can see that this green simulated curve here, actually, is that the green one that we're seeing there? Yeah, it is. Okay. So if you look at what that structure, that's projection looks like with that sort of close to Schetzer defocus, I didn't figure out exactly. Schetzer is somewhere around 0.04 or 0.02, 0.03. I don't remember exactly off the top of my head, but you can see that you wind up with the projection, which actually looks very much like the particle itself. Right, so that there's very little CTF impact until you get out to pretty high resolution. And the goal of Schetzer defocus is basically to push this out to very high resolution. So then if you're doing negative stain with that, you just don't have to worry about the CTF at all, really, other than the fact that it's doing a little bit of a high pass filter on your data. And if you had a phase plate, then you could eliminate even that. The trick though is that when you get really close to focus like this, that your contrast is massively reduced, right? So you can see how much signal we're getting here from the red curve. The total contrast, the sort of the integrated area under the curve, the green curve is just going to be meaninglessly small. If you're working in negative stain and you can use pretty much as much dose as you want, doesn't matter. You can just dose it high enough that you can get the signal to noise ratio way as high as you'd like. But if you're working in ice, then you really can't afford to work really close to focus like this unless you've got a phase shift to shift the if we put the phase shift in here at 0.5, right? So if we put in a 90-degree phase shift there, then you can actually get this sort of beautiful curve. It's got very strong contrast and everything like that. That's sort of the idea, behind the phase plates. You can get rid of this high pass filter effect. It comes at a cost, but you can do it. All right, so let's put this back to 10% amplitude contrast. Right. So we need to pick our defocuses in a sensible sort of way. So I guess what I'm saying here is we want to probably, if we pick our defocuses sort of across a range between 1 and 2 or 1 and 1.8 or something like that, if we continuously cover that range, we can make pretty smooth a pretty smooth black curve. So our final average structure, every place where you see a little dip here would correspond to a place where you might see a little bit of a dip in your FSC curve when you get your final structure out, because you've got more information in aggregate across all the images here than you do here. Okay, so our goal here is just sort of to determine parameters, and then we'll go back to our Jupyter Labs session to actually try and apply the CTF to this. So another way we could have tackled this, and I use the other tool so we could compare different defocuses all at the same time, is we could use E2 filter tool and apply that to the projection stack. And actually, look, I've already got it set up here. So we've got 2 processors. We've got math.simulate CTF, and we've got math.add sig noise. So if you're working in Python, you actually could just directly access the CTF objects and you could do stuff yourself manually. But if you're working from the command line, or if you're working using any of these graphical tools, then you want to have it implemented as a processor. So there's a processor that basically just implements the stuff that you need for the CTF simulation stuff. Now, I'll note that there is a noise amplitude available inside this math.simulate CTF. And in my experience, it doesn't seem to work right, but I never actually sat down to really take a look at why it wasn't working right. So there's an option. So I'm just using a different processor here, which will add flat band random noise to the data. Flat band noise isn't really a good approximation of what you get out of the microscope. The noise you get out of the microscope is kind of pink, right? It's stronger at low resolution than high resolution, but for our purposes, it'll be fine. So if I check this, I can simulate the CTF on a bunch of these images all at once. But I can only simulate a single defocus at a time. So here it's 1.5 microns. So I'm leaving that at 0 because it's not working right. 300 volts, so 300 kilovolts. I've got the amplitude contrast set to 5. We can make that 7 or 10, whatever you prefer. You can see it doesn't have a tremendous visual impact. B factor of 100 is probably fine for anything that we want to do. We don't. So this is checked, but it's set to 0. Basically, it's disabling this option. We don't want to use that option. That option is used when we're doing specific stuff with bispectra. I have the C sub S set here to 0.01. We could make it 0.001 or something. So if you have a CS corrected microscope, which an increasing number of people do nowadays, then the C sub S is effectively 0. But you can't put in exactly 0 because it makes certain equations singular. But if you put it in almost exactly 0, then it's a pretty good simulation of the microscope. See anything else there? I mean, we can set that, but it's already defaulting to the right value, so it's fine. Okay. So anyway, so that's the CTF application. Now I could just use this filter tool here, and I could apply. Oops, hang on, sorry. I think this is a Mac thing. Yeah, you have to like switch back and forth somehow between things before. There we go. And you could say save process stack, and it would apply this filter to that whole stack of data from the GUI if I wanted to. But then we'd have the same defocus for all of the data, and we don't want the same defocus for all the data. We'd like to chop it up into groups or something like that at least. The other thing we have to do is figure out noise parameters. So here we'll go ahead and turn that on, and then we can adjust the slider here to sort of pick a level of noise which we think is reasonable for our data, right? So just visually pick. Let's see what happens with 10. So 10, that may be beginning to get a little bit too strong there. So maybe I want my particles to be kind of somewhat visible still. So somewhere around 5 or 6, maybe a reasonable level to kind of simulate single particle data. it's not always necessarily going to be 5 or 6. So you want to actually sort of test it against your data, because it depends on the amplitudes that are present in the data itself. So if I had simulated the data and I had made the data have twice as strong amplitude, then I would also actually, well, this is in terms of standard deviations. So the absolute amplitude shouldn't matter, but the way I'm filtering the data might matter. Anyway, so this value does actually require a little bit of testing. You don't want to just assume that it's okay. If we now, let me go ahead and do this. I'm gonna add a 2D view to the filter tool program. So the filter tool program can show you the stack view. It can also show you the single 2D view. And the usefulness of that is that you can open the control panel on this and then get access to the various tools that are available here, which wouldn't be available in the control panel here. And now I can compute a power spectrum for the stack of images here. And let's turn off the noise. And I'm going to compute a power spectrum again. And then let's turn off the CTF. And then we'll do, where did my window go? There it is. And I'm going to do the power spectrum in the stack again. Okay, so now we've got 3 different power spectra that we can look at. Now, it would be useful if we could get all these in the same window. There's a trick we can use for that. If we open the control panel for each of these. Oh, there it is. Sorry, we just wound up on top. We can actually grab from this list, and you can drag it into the list of another window. Oh, uh-oh. Used to work. Oh, there it is. Oh, all right, fine. I just had to click to make it show up. Okay, fine. Okay, so then we can get all 3 curves in the same window and we can compare them. So let me put this on a semi-log scale again here. And now you can see that without the CTF imposed, you've got the blue curve. With the CTF imposed, but with no noise, you've got the red curve there, right? So it's very damped at low resolution. And then it's got the CTF oscillations, and then it sort of falls off towards 0 at high resolution. The reason this looks parabolic is because we're using a Gaussian B factor, right? We have a B factor, and the B factor is a Gaussian. So if you plot a Gaussian on a semi-log scale, it looks like a parabolic curve. And then we have the green curve, which is with the simulated CTF and the noise at. So that doesn't fall off to 0. It's just what you're seeing here is sort of the flat band random noise at high resolution. So if we zoom in on the green curve a little bit here, you can see that the noise begins to sort of overwhelm the signal very quickly in here. Anyway, that was just for fun, for visualization. So we've got our parameters, I think, pretty well. We already knew what parameters we wanted to use for defocus, and now we know that our noise should be somewhere around 5 to 7 to 8, something in that range. So now we can quit filter tool, and we can cat the filter tool parameters, right? So we can see the processor arguments here, which we could use either in the with other command line programs. Or in our Python scripts, we can adapt these into a dictionary.
Sorry, Dr. Lucky. So did that save that text file generate automatically when you close the program?
When you use filter tool, every time you adjust the parameters, it updates that text file. So when you quit filter tool, for each different set of filters that you have set up, it will store it. This is both useful by the user directly, because you can look at these parameters, but this is also if you run filter tool again, and it shows you all the options being the same again, those options are actually drawn. It parses the command line and turns them back into options again. So if you edited that text file and you put in different values or something, then the next time you ran filter tool, it would have the updated values. All right, so let's, I'm going to copy that and copy that just so I don't have to rearrange my, so I don't have to rearrange my windows. And then I'm going to go back to my Jupyter Labs session here. Okay, so we've written out our 10,000 images here to proj.hdf. So now we're going to have to sort of read them back in if we want to do anything to them. Probably makes sense to do these, do it sort of one image rather than reading all 10,000 images and processing them and writing them out. Probably makes more sense to sort of read them one at a time and process them and then write them to a new file. I guess one question we could ask is whether we want to, what sort of CTF processing we want to do. Do we want to just take the simulated data as it is and immediately be able to play with it in the dynamics tool, or do we want to actually run it through single particle processing and then run the dynamics tool on the result of the final reconstruction that we get? Sort of thinking about it. If we do a reconstruction, obviously it's going to take a little time for the reconstruction to run. I mean, not days or anything, but it'll take more than the amount of time we're going to be standing here today to run. Maybe that's not a bad thing to do though still. So maybe we should generate some data and I'll reconstruct the data. And then next session, we can load the data that we reconstructed into the dynamics tool. And we've already gone 35 minutes or something. So, so let's go ahead and do that. We don't need this. We don't need this. So we're going to say, we know there's 10,000 of them, so I'm just going to assume that for I in range 10,000. Now we have to decide how we want to break the defocus up. If we're going to try and do reconstructions or processing on this, we want to sort of simulate the data being in different micrographs and each micrograph having a different starting defocus associated with it. Meaning that or average defocus associated with it. So, it might be that each particle would have a slightly different defocus. If we wanted, we could try and simulate that too. I'm not going to bother, but I want to break these up and say maybe, I don't know, 200 particles per frame or 500 particles per frame, and then each frame would have a different defocus. So, so let's do it this way. We'll break it up into groups of say 250, that arbitrary number. And then within each group of 250, we'll use a different defocus. So we'll go from I to I plus 250 in here. And let me just make I could do it in Python, but it's easier just to do here. So I'm going to make a folder called particles. I'll probably shift that folder into another subfolder so we can make like an EMAN2 project where I'll run the refinement and stuff. But for now, we'll just call it particles. Let's see. Now we'll say image is emdata proj.hdf. And we're going to read that the image number is going to be J, because each of those 10,000 has a different orientation and that sort of thing, and other parameters. And then we want to apply these filters that we just figured out, the processors that we just figured out. So let's just paste those things in here, and then I'll adapt them into Python code. Okay, so we'll say im.process in place. This is the only thing we're going to do with the image, so we might as well overwrite it. And the processor is going to be math.simulate. Now we want to make sure that we do the CTF simulation first and then add the noise second, because if you add the noise first, then the noise is going to get filtered by the CTF, and then you're not going to have any noise at the places where the CTF is 0, and that's not realistic. Normally you'll have noise, just as much noise where the CTF is 0 as where the CTF is high, so it wouldn't be a good simulation. Okay, and then we need to give amp count 10, B factor 100. That's fine for what we're going to be doing. We don't necessarily have to specify all these things, like bispectrum FP will default to 0 anyway. We can go ahead and specify C sub S. And let's use a more typical C sub S 2.7. Let's see, noise amp 0, phase flip 0. Yeah, so if I have phase flip set to 0, that means that it won't actually be flipping the phases. So if we process this data following the standard EMAN pipeline, that means that we would want to skip the CTF correction part of the process. I think I'll go ahead and just make this a full processing pipeline. So we'll go ahead and say phase flip 1. So we're going to flip the phases, and then when we do the processing, we'll unflip the phases. I'm a little worried that I may not have used a big enough box size for this data, because it's filling pretty close to the edge of the box. So maybe I'll tweak things a little bit more. All right, so we'll go at C sub S7, phase flip. I figure any additional little tweak I put in here is extra knowledge that you guys are getting, so we might as well play around a little bit. So phase flip will set to 1. Voltage 300. Anything else? Defocus, we need defocus. So then defocus, we want that to be random per micrograph. So we'll say defocus, close, that. Then here, on each of these simulated, micrographs, we'll compute a defocus or determine a defocus. And I think we had already imported random, right? So we were using random.random here to make a choice, and I think somewhere else we were using random. Oh, we were using this random here. That's fine. We can just random dot random, which will give us a value from 0 to 1, and then we can just multiply it and add it to whatever we want. There's another random generator that we could use, that like uniform or something, and we can give it a range, but I'm just going to do it this way. So we're gonna use a range of 0.8 and have a minimum value of 1. So this should give us a random number from 1 to 1.8. Oh yeah, I said I wanted to make the box size a little bit bigger because we don't have any. Basically, the images are 0 outside the particle that we've simulated. We don't have any background present already. We can easily just pad the box, and there shouldn't be any real artifacts at the edge or anything like that. So I'm going to say, I'm going to go ahead and just put it in here. I'm going to say get clip region, and I want to make, I think the box size now is 256. So let's look at our list of good box sizes. I mean, I know what they are, but e2 help.py box size. So we'd like to use a box size from this list. So we have 256 now. Maybe 300 would be a good choice. That's not too bad, or 288, 320. So probably one of these would be a good choice to make it a little bigger. Let's go with 300. 300 is not a bad box size. So if we have 256 and we want to make it 300, 300 minus 256, 44, so 22. So we need to offset by, we want to start at minus 22. And then we want to make the size 300 by 300 like that. Now, actually, sorry, these are 2D, not 3D. So just variables like that. So region allows you to specify either 2D or 3D regions. If you're specifying a 2D region, this is the X and Y starting location, and this is the size of the resulting box. So if you want to pad something that's 256 by 256 and put it in a 300 by 300 box, you have to shift the origin past the origin, sort of outside the box, and then you specify a bigger box size, and you want to make sure that the size in the lower left is the same as the size in the upper right. So it's 300 minus 256 divided by 2, which are the negative numbers that you see right there. Hope that makes sense. Okay, so this will shift our 256 box to 300, simulate the CTF. We're using the defocus that we computed up here, and we'll only change every 250 particles. And then im.process in place.
This isn't super critical, but just so So I'm connecting dots. Is that get clip the same function that E2 proc 2D and 3D are calling when you do the clip?
Yeah, if you say clip in E2proc 2D or E2proc 3D, it uses get clip to accomplish the task. Yes.
Gotcha.
So get clip can be used to make things either smaller or larger. It's used for arbitrary subregion extraction. And if you go outside the box, it will pad with zeros.
Gotcha.
Process in place. Okay, so here we need to add the noise. Math.add sig noise. And noise is equal to, I'm going to go with 7. I guess I could use different noise levels for different images if I wanted, but we'll just use a single self-consistent noise level. Okay, and then once we've got our image processed, we need to write it back to disk. And since last week, we have fixed the write image notation so we can specify the number of bits we want to keep in the final image. It was kind of working funny last week when I said :8 in the file name. It was doing funny things. So I can say write image particles / right, so I need to use a format string here. PTCL, maybe just image underscore, and then this is going to be the micrograph number, which I guess J divided by 250 should give us a good image number. And I probably want to 0 pad that. So if I have 210,000 divided by 250, I'm going to wind up with 40 different micrographs to worry about. So I need 2 digits. So 0 to D here. And I'm going to, oh yeah, and I want to put a :5 in there. So when we published that paper about compression recently, the number of bits that you're supposed to need to keep for your data to make it, to retain everything that's actually present in the original data, 5 is supposed to be pretty much safe for everything. So I'm going to use 5 bits here, and we'll see if everything works out the way we hope. See anything else? Then we need the image number, which is going to be, oh, this is the image number within a micrograph. So we want to say J minus I here. Okay, now you could, instead of just having one variable and like have this variable range from 1,000 to 1,250 or something, we could have had a second variable which is sort of counting how many micrographs. But it's easier just to sort of do the math. That way, if we adjust our loops, hopefully we won't make any mistakes or anything. So here we can use J to compute. Oh, actually, we should have used I here, not J. I divided by 250 should give us which simulated micrograph we're on, and then J minus I should give us the image number within the simulated micrograph. Okay. I think that's everything. So if anyone sees anything here which they think I missed, tell me. And if anyone has any questions about any of this, ask. That's what this is about, right?
I'm just impressed that you did it so quickly. It's sort of taken me a second.
So I've been doing this for a long time, unfortunately.
Yeah.
Okay, well, we'll just go with this and we'll see if it works. Well, actually, it should have crashed because I hadn't imported EMAN yet. Not sure why I didn't give an error though. Huh, it's kind of weird. All right, I'm going to go ahead and import EMAN, and we're going to try it again and see what happens. Well, that's weird. I'm not seeing anything. I'm not seeing error messages here, which something funny going on with my Jupyter session or something, I guess. All right, I'm going to just shut down my Jupyter Lab session here completely. And we'll start it up again and see. See what's going on. Okay. Okay, that's good. Okay, that seems good. Okay, something in my Jupyter installation seems to suddenly be broken or something. Let me try.
Hello world.
Let's do this. Well, that worked. Oh, that would be the problem. See, I don't write perfect code. I said range 10,000 to 250, which would start with 10,000 and loop until it gets to 250, but stop before 250. So it got to this and it just immediately stopped. So it was never even trying to get to this other code, which is why it wasn't producing any output. So there you go. Let's try again. Ah, there we go. At least now we're getting an error. Oops. Ah, I forgot the HDF in my output file name. That would be a problem. Particles image dot HDF :5. Okay, one more try. Good, now it's working. So we should now see if we look in the particles folder, you can see we're gradually getting new image files showing up there. And if we do E2 display, and we look in the particles folder, each one has 250 images in it. And they look like this. So there's the first image. It looks like that. We should have a different defocus for the next image. So you can see the defocus looks at least a little bit different in each of these. Maybe you can see that, maybe you can't, but it is. Okay, so it looks like it's working as expected. Still running, but it's probably almost done because you needed to make 40 based on our computations. So okay, all done. So we have now generated our simulated particles, which have full defocus applied to them, and the orientations are random, but the shifts should already be correctly set. Now, I guess the question is, when we do the reconstruction, since the particles are sort of highly variable, whether we're going to have to do anything to account for that. I mean, I'll do a C1 reconstruction, obviously, because I could start with D8, start with D7, the symmetry of a normal Groyel. But since in the end we need to end up with C1, it may just start with C1 in this case. All right, so I'm going to shut this down. Okay. And I'm going to make a folder called recon for the reconstruction. And we're going to put the particles into recon. And then I'm going to try and do a canonical EMAN2 reconstruction using this. So I'm going to start out with E2 Project Manager. And I'm just going to be following stuff from the tutorial here. So I'll get sort of the first step started here, and then we'll end the session for today. And then next week we'll try and import that session into the GMM tool. Okay, so we'll start by making sure the project settings are good. So we want 300 kilovolt microscope, 1 angstrom per pixel, 2.7 C sub S. Then raw data, we shouldn't have to do anything. We've already imported our data. Oh, that's the TOMO mode, sorry. Single particle reconstruction mode, raw data. We've already done that stuff. Particles, we've already got our particles picked, so we're on to the CTF step. So we're going to say CTF auto process, and we're going to say we're targeting high resolution. And these values were filled in because I just set them in the project. And it should automatically find the particles, because I'm going to say it's going to work on all the particles in the particles folder. So all the files in the particles folder should get auto processed. Then there are options we can use in the CTF fitting. I know my defocus is from 1 to 1.8, so I'll narrow this range a little bit. Oops, 0.8. And
Is that just a time saver?
What, for setting the range?
Yeah.
I technically it's not really going to save any measurable amount of time either. But if you know the range is constrained in a given region, sometimes if you give it a range of say 0.1 to 6 or 7 or something like that, sometimes it may mistake one of the low resolutions structure factor oscillations for a CTF oscillation or something like that. So there's certain structures where you may get a discrete incorrect defocus in a discrete way because the structure factor has some oscillating characteristics. It's very common for virus particles, which have a lot of high frequency harmonics in them, or sorry, low frequency harmonics in them, I guess is what I should say. Most projects, it's not a problem, and it just sort of gets them all right. But anyway, if you know it's in a range, you might as well use it. I don't have to say from scratch because it doesn't have any information on the defocus now. It'll do it from scratch anyway. I don't think I need any of these other things. We didn't flip the contrast of the particles, so I don't need to unflip them. Yeah. So if you had done an initial defocus estimate on the whole micrograph, then you could use defocus value from the micrographs instead of from the particles, and sometimes that's a useful thing to do. But we didn't simulate micrographs; we just simulated particles. So anyway, so we'll just go ahead and launch this. And we can watch here in the command line. We can see it's determining all the defocuses. And it's coming up with reasonably self-consistent maximum resolution estimates. We don't try to compute these really precisely, but it'll often give you a decent ballpark estimate. You can see the B factors that we're getting are, at least in the general ballpark range of 100. So it's fine. The B factor isn't actually used for anything in the reconstruction, so it doesn't really matter if it's wrong, but so we'll just let this finish. It shouldn't take very long. Once it determines all the defocuses, then it's going to, I didn't tell it to use any threads. All right, so it'll take a little longer than it should have because it's going to do it once, single threaded, but it won't take that long. Okay, so now it's determining a structure factor estimate from the set of particles. And now it's writing the output. Oh, actually, so no. Oh, sorry. Now it's redoing the defocus determination using the structure factor that it just computed to try and get a little bit better. And once it finishes that, then it'll write all the output files. So if we look, yeah, go ahead, ask.
I was going to say this may be a good opportunity just for me to get a little bit more of the history, because CTF has been sort of historically, that was a big limiting factor for resolution determination for a long time. And it seems like there were, well, first off, am I right in that how you compute it? People compute the CTF differently in different programs, right?
People determine the CTF with different programs.
Right.
You're right. There was like a CTF determination challenge,
right,
12 years ago or something like that, where different software packages for determining the CTF were sort of competed against each other. The one that people use most often nowadays from Nico Grigoriev's lab for sort of whole micrographs. At the time, it was viewed as it came out with very accurate results, but it was extremely expensive computationally to run at the time, right? I mean, your computers were 100 times slower back then.
Right.
So it was basically doing an exhaustive search of every possible defocus and other parameter on whole micrographs. So it was very expensive, but it tended to find the right local minima because it was basically checking every point.
Gotcha.
Some of the other tools, like the EMAN tool, were faster and more efficient, but occasionally they would get it wrong in certain types of cases. I would say it's not really an issue nowadays. That pretty much all of the tools that do this do a pretty good job at it. It's a good idea always to sort of double check and look at least manually look at least a few of the resulting a few of the resulting CTF curves and stuff, and make sure that they look sane, regardless of the tool that you're using. But it's not really a limiting factor for anyone. It hasn't really been a limiting factor for anyone for a decade.
Yeah. Okay. Yeah. And I was speaking more historically just to try to
Yeah.
contextualize.
I mean, historically, I would never say. I mean, so 25 years ago, no one did CTF correction in single particle analysis, and everyone was just sort of stopping at the first zero of the CTF, which was typically at about 25 angstroms. And that was the resolution that people were achieving in their structures anyway. It was all being done on film, and micrographs were getting scanned. And the state of the single particle analysis field in the late 90s was sort of everything was just these sort of 20 to 30 angstrom resolution blobograms, right? Around 2000 is when people transitioned to actually starting to do CTF correction at all, and the data was getting good enough that you could actually get some benefits out of doing that. And then there was a period of a few years where people were sort of deciding, oh, what are the best tools to do the CTF? Anyway, so historically, there's sure a lot happened back then, but nowadays it's only of historical interest.
Okay. And the current way, like, is it? I know that the current way that EMAN2 calculates the CTF is from, like, you guys have like a paper in like 2016 or 2014, I think, talking about the algorithm. Or
I don't think we've changed it. I mean, we did. It is in a paper somewhere, but I don't think we've changed the CTF determination in a long time, really. I mean, we added whole micrograph defocus estimation at one point, just so people could get sort of initial estimates and look at their data quality more easily. And it can be useful to get that as sort of a hint in particularly difficult cases, but I would say in 90% of projects, just running the automatic tool is fine. The other 10% of projects, there will often be some kind of artifact. Either the contrast is really weak because the ice was thick, or there's some funny structure factor feature which confuses things or something like that. So there are occasional cases where you may have to tweak some parameter or something to get things to come out okay. But it's not really a major factor for anything. Now, when you're talking about really pushing the resolution, past 2 angstroms to high resolution, you start having to think about per particle defocus correction and stuff like that. But that's not something that you handle at this stage. That's something that gets handled during the refinement stage, where the defocus values for individual particles might get tweaked. And if you do that, you then have to sort of undo the CTF. If you do that in the canonical way, where you flip the phases once you've determined the defocus here in EMAN, then you have to sort of unflip the phases and then flip them again with the correct defocus, something like that. Anyway, I guess what I'm saying is there are some cases where there are complications to what I'm saying, but for 2 to 2.5 to 3.5 angstrom resolution reconstructions of typical particles, it's not something to worry about.
Right.
Okay, so we can see now in this particles folder, now we're getting all these other files. So this was the file that we gave it to start with. Then it makes the full resolution CTF phase flipped output file. And then it also makes these other downsampled files for convenience to make refinement runs and stuff run faster. you don't necessarily have to use these at all. You can just sort of jump straight to the full res data for certain cases. It just sort of depends. Most of these other files and stuff is about making things go faster rather than about getting better final results. For the final results, you'll always use the full resolution data. All right, so we've gotten to be after 1 o'clock already here, and I guess it's almost oh no, sorry, it's doing the last type of file now. Yeah, it's still gonna take a few minutes to finish. So I'm gonna go ahead and just run a canonical refinement after the CTF stuff finishes, and I think we'll just call the session for the day, and then next week we'll get back to it. I'll post the Jupyter Lab notebook again, and if people want to do some of this on their own machines, you can basically just follow the EMAN tutorial and on this simulated data, starting with what I just did here, and you know, reconstruct this synthetic GrowEL for yourselves and see how it works out for you. But then next week we'll try and run the Gaussian mixture model tool and see if we can do the dynamics analysis. Any other questions or comments from anyone else?
I was just curious, if you wanted to simulate tomography data, would you kind of do that at the step of when you're generating the projections, just generate like a set of related projections and then continue?
So the question there would be, would you want to simulate whole tomograms, or do you want to simulate tomographic tilt series for individual particles?
For individual particles.
Okay, yeah. So then you could do it very easily. Just modify the program that we made last week and make it so, yeah, you basically make a tilt series for each particle.
Cool.
You would have to, you know, if you wanted to use that data in the EMAN2 single subtomogram averaging pipeline, you would have to generate a simulated 3D particle and a simulated tilt series for each simulated particles. You'd have another nested layer in your nesting layer in your loop, right? So you'd randomly orient the 3D particle, you'd save that to a file, and then you'd have another loop where you generated the tilt series for that one particle and save that in another file.
Okay.
But yep, fundamentally it's about the same. The other thing is obviously you'd add a much higher level of noise to the raw particle data.
Mm-hmm.
Yeah.
Cool. Thanks.
Okay. All right. No one else has anything? Then I think we'll call it for today.
I did have one more question.
Go
We
ahead.
have time.
No, it's good.
So when I look at a lot of the CTF fits, you see the estimation goes out to a certain resolution. And I was just wondering what the fate of the information past that resolution is. Does that just get discarded?
No, I mean, there's actually the sort of the B factor that gets determined doesn't actually get used anywhere in EMAN. I mean, I guess there's one place where it might sort of be used, but it's not going to act as any sort of a cutoff to your data or anything like that. The estimate that it's trying to give there is just sort of the point at which the signal to noise ratio seems to fall below sort of a threshold value. And based on past experience with kind of all the different packages, once the signal to noise ratio, the spectral signal to noise ratio, right, as a function of frequency, once that falls below around 2%, 2 to 3%, then none of the alignment algorithms or software that's out there can really recover that signal anymore, right? So once it gets below 2 or 3%, you just can't do alignments based on such noisy data, and that will wind up being kind of a limiting resolution in your final reconstruction. You know, when you do your CTF estimation with Nico's software, it actually takes that sort of one step further. Our estimate was just sort of based on signal to noise ratio, where it can see stuff. The estimate Nico software makes is based on how accurately the defocus can be determined. So that means that you may be beyond that resolution, you may be inaccurately doing the phase flipping. And that has a really serious effect, because that means that if you'll have a mix of data that has sort of positive phase and negative phase, and then it might actually contradict itself when you try to do the reconstruction past some resolution.
That's
So,
sort of what I
the
was
resolution
wondering
cutoff
about.
you get from that software may actually be a serious limit that limits you. But the value you see in EMAN is just sort of kind of a rough data quality estimate. It's not, you shouldn't take it as seriously.
Okay, thanks.
Yep. Okay, great. I'll see people next week.
Thank you.